This is how a step signal looks in a PCB trace. But why does it look like two steps instead of one? That is because I have made this trace intentionally long so it behaves like a transmission line and we can observe reflections. And this can ruin your day if you are not paying attention when designing your PCBs.
Hi, welcome to Markestronics. In this channel, we talk about electrical engineering and PCB design. In this video, we will talk about transmission lines in a printed circuit board.
Let's start with a little bit of theory. According to Wikipedia, in electrical engineering, a transmission line is a specialized cable or other structure designed to conduct electromagnetic waves in a contained manner. Based on this definition, any trace may seem like a transmission line. So let's keep reading. The term applies when the conductors are long enough that the wave nature of the transmission must be taken into account. Okay, so things get more interesting now. It means that the length of the trace matters. In order to consider a trace as a transmission line, it has to be long. But how long? Well, there are some rules of thumb. For analog signals, many agree that if the trace is longer than 1/4 of the signal's wavelength, it's considered a transmission line. But for digital signals, as they are typically composed of a wide spectrum of frequency components, a definition based on a single wavelength is impractical. In that case, we use two parameters, rise time and propagation delay. The rise time is the time it takes the signal to go from low to high. Propagation delay is the time it takes the wave to travel between the ends of the transmission line. A well-accepted rule of thumb for digital signals is that if the propagation delay is longer than the rise time of the signal, then it can be considered as a transmission line. But these rules of thumb are not an exact science. Multiple authors and designers use different values for these parameters, so don't take them too seriously. What are the problems when a trace behaves like a transmission line? The answer is reflections. When light, another type of electromagnetic wave, encounters a discontinuity, such as transitioning from air to glass, part of its energy is reflected, while the rest is transmitted into the glass. A similar thing happens to electromagnetic waves traveling between conductors. When they see a discontinuity, for example, a change in impedance, like the case when a signal goes from a PCB trace to a load resistor or to a digital logic input, part of that energy is reflected, and the remaining part goes through the load. These reflections can reach the transmitter, causing voltage spikes that could be harmful to the circuitry, and bounce back to the receiver, causing false triggers. In order to observe the effects of waves in a PCB trace, I have designed in KiCad a very simple board with a single trace, but I have made it very long intentionally. That way, the trace is no longer an ideal interconnection and rather behaves like a transmission line. Here I have highlighted the trace. Note that I have added a lot of wiggling around the board to achieve the greatest length as possible while keeping the board at a moderate size. In this case, I have managed to route a trace that is around 3.5 meters long in a board that is only 10 by 20 centimeters. I have added 3 BNC connectors, one to serve as input labeled in1, and a couple of output connectors labeled out1 and out2. The input connector will be connected to a function generator, and the output connectors out1 and out2 will be connected to channels 1 and 2 of the oscilloscope respectively. Out1 is placed very close to the beginning of the trace or the transmission line, and out2 is connected right at the end of the transmission line. The main electrical properties of a transmission line are its characteristic impedance and the propagation delay. I designed the trace to have a characteristic impedance of approximately 50 ohm. In order to define the geometry required to achieve 50 ohms, I used calculator tools in KiCad, which you can find in the home window, clicking on calculator tools. Here under the high speed section, you can click on transmission lines, and it will prompt you to enter certain values or parameters in order to calculate the geometry of your trace to achieve a specific characteristic impedance. For transmission line type, I chose coplanar waveguide with ground plane, which is the structure that I chose for my PCB trace. In the substrate parameters, I selected an epsilon sub r of 4.5, which is the dielectric constant of the FR4 that my manufacturer provides. The H parameter is the dielectric height, or the thickness of the FR4 basically. So I chose 0.8, which is the value I decided to use in my design. T is the thickness of the copper, which is, for my case, the standard 0.035 millimeters. Under physical parameters, you will find the W, or width, which is the width of your trace, but this is what you want to calculate, so initially you just keep this blank. Under S, this is the spacing between the trace and the surrounding ground plane, for which case I have defined 0.2 because that is the value that I entered in my PCB design in KiCad under the design rules. L is the length of the trace. This parameter doesn't affect too much for the characteristic impedance, but it is important to obtain the propagation delay later. So I just entered the length of my trace. The total length of my trace is 3,474 millimeters. If you want to know the length of your trace, you can go to your PCB design, select the trace, and here in this area on the bottom region of your window, you can see this routed length value. So I took the value from here, 3,473. Under electrical parameters, you input your desired characteristic impedance, in my case 50 ohm, and when you click on synthesize or this up arrow, this calculator tool will return the width that you need in order to achieve that characteristic impedance that you selected. So let's try it. So when I click synthesize, I get a width of 0.84 millimeters and a unit propagation delay of 53.33 picoseconds per centimeter. I rounded up this width to 0.85, and that's why you see a trace width of 0.85, which you can also see in this region on the bottom side of the window in the PCB editor of KiCad. So using this width, you get very close to 50 ohm impedance. In this case, we can now do the opposite just to confirm how close we are to the ideal value. So if I enter 0.85, which is the trace width that I actually used, let's see how close we get to 50 ohm. So according to the calculator, we get 49.76 ohms, which is pretty close to 50 ohm. Once we have found our trace width required to obtain 50 ohm impedance, we need to also calculate the total propagation delay of our transmission line so we can model it correctly. The calculator gives us the unit propagation delay, which is the propagation delay per unit of length or distance, in this case in picoseconds per centimeter. So in order to obtain the total propagation delay, we just need to multiply this value times our total length. So 53.36 picoseconds per centimeter times 3,474 millimeters, and it will give us a total propagation delay of 18.5 nanoseconds approximately after doing all the appropriate unit conversions. If we take into account the BNC connectors, the cables that we are using to connect the board to the oscilloscope, our total propagation delay observed in the experiment is going to be probably closer to 20 nanoseconds. And that's why I have labeled in my silkscreen TPD, or time propagation delay, of approximately 20 nanoseconds. Instead of jumping right into the practice, let's perform a simulation first. That way we can compare our results with what is expected according to the theory and the math. To do that, I'm going to use LTspice, a free circuit simulation software based on SPICE, developed by Linear Technology, now acquired by Analog Devices. I placed a voltage source sending a pulse that simulates the function generator. The pulse amplitude V on is 1 volt, and the T rise and T fall parameters, which represent the rise and fall times of the function generator, are 4.5 nanoseconds. I also placed a 50 ohm resistor in series with the voltage source to simulate the output impedance of the function generator, which is 50 ohm. LTspice has a circuital model for transmission lines, which is what I use to simulate my PCB transmission line, T1, and I have defined its parameters as TD, which is the propagation delay, as 20 nanoseconds, and Z0, which is the characteristic impedance, as 50 ohms. I also terminated the transmission line on a 1 megohm resistor to simulate the impedance of the oscilloscope inputs. If I run the simulation by clicking on this green play icon and click on both ends of T1, we can plot the waveform produced by this simulation. The green line represents the signal at the beginning or the start of the transmission line, and the blue line represents the signal at the end of the transmission line. We can see that the blue line is kind of what we expect, a 1 volt step signal after 20 nanoseconds, which is the transmission delay of the transmission line. But the green line doesn't make much sense. It rises initially up to 0.5 volts, stays there for almost 40 nanoseconds, and then it rises on a second step to 1 volt. Why does it happen? The answer to this is reflections on the transmission line. To explain what's going on, I have prepared a simple animation, and please forgive my animation skills. Here, this yellow step signal starts at the top left of the board on the input connector and will start to move along the trace. But while the signal is propagating through the trace and until it reaches the other end of the transmission line, it sees the trace as a 50 ohm load. It doesn't know yet that at the other end of the trace there is a oscilloscope with a 1 megohm input impedance connected. So the 50 ohm will form a voltage divider with the 50 ohm source resistance of the function generator, and that's why we see initially a 0.5 volt step on this green line in our simulation. Remember that this green line represents the voltage at this initial end of the transmission line, which is in the board will be represented by the out1 connector. So let's play the animation and see what I just explained. The signal starts to propagate, and during this time it is only seeing the 50 ohm impedance of the trace. It hasn't reached the other end, so it cannot know what load impedance is connected there. So here, after 20 nanoseconds, it reaches the other end. Here, when the signal hits this end, it suddenly sees a 1 megohm impedance that will cause a reflection. The amplitude of this reflection can be obtained from the reflection coefficient equation, defined as rho, which is equal to Z load minus Z0, divided by Z load plus Z0. The coefficient can be any number between -1 and +1. A reflection coefficient of 0 means nothing is reflected. A rho of +1 means the full wave amplitude is reflected, and a rho of -1 means that the full amplitude is reflected, but with the opposite polarity. Any value in between represents the proportion of the incident wave that is reflected back to the transmission line. Using the values of 1 megaohm for Z load and 50 ohm for Z0, we obtain a rho of 1. This means that the full wave of 0.5 volt is reflected back to this trace. So after 20 nanoseconds, the 0.5 volt step signal has reached the end, immediately reflects back, adding up to the incident wave another 0.5 volts. Here at the output 2 connector, the incident and reflected wave add up immediately, producing a full 1 volt step, which is what we see here on the simulation in the blue line, that after 20 nanoseconds we observe a 1 volt full step, which is the result of the 0.5 volt incident wave and the 0.5 volt reflected wave being added up together. And now the reflected 0.5 volt wave starts to propagate back. So let me hit play to observe the reflection being propagated back to the source. So after another 20 nanoseconds, for a total round trip of 40 nanoseconds, we observe the voltage at the out1 connector jumps another 0.5 volts to finally reach the 1 volt of the original signal. So that explains why the green line after 40 nanoseconds jumps another 0.5 volts to reach and match the full 1 volt of the original step signal. So here's the actual board. Very simple. You can see the BNC connectors. They are standard 50 ohm BNC connectors. You can also see the trace meandering around the board. So it's a single trace with over 3 meters long. On the other side there is just a solid copper plane, and I added some equations on the silk screen, some information about transmission line geometries like microstrip, strip line, etc. Some useful equations that I use in this video, and also the stack-up table if you want to replicate this layout with a 50 ohm impedance. I will leave the links in case you want to download the files for this board in the description of the video. So I have connected everything. You can see the coax cable coming from the function generator entering into the input connector, and the two coax cables going from the output connectors to the inputs of the oscilloscope, channel 1 and channel 2 respectively. And you can see the output waveform on the oscilloscope. Now, in order to analyze better this signal, I will download this capture into a pen drive and analyze it on the screen because my filming gear is not very professional. I have downloaded the screen capture from the oscilloscope to my computer, and I have placed this image side by side with the plot we obtained from LTspice during our simulation, so we can compare the results. The yellow line on the oscilloscope capture is the equivalent to the green line on our simulation, and the purple line corresponds to the blue line on the simulation. So you can see that the yellow line starts rising up to approximately 0.5 volts. You can see that the scale is at 200 millivolts per division. So this yellow signal rises up approximately 2.5 divisions. So that's roughly 0.5 volts. It stays there flat for some time, which we will see next, how much time approximately that is. And after some time, it rises up to the full 1 volt of the original step that we injected to the trace, which is similar to what happens on the simulation. The signal rises up to 0.5 volt, stays flat for some period of time, and then it rises up another 0.5 volts to finally reach 1 volt. Of course, there are some overshooting and ringing on this real signal because this is a physical board with some imperfections or non-idealities. Remember, in a simulation, all the components are ideal. They don't have parasitic capacitance, inductance, or nothing, none of that. Everything is a perfect component, an ideal component. In the real world, you are going to observe some artifacts on your signals, but the overall shape of the signal matches what we observed on the simulation. Also, the purple line, which represents the blue line, and it rises up after some delay respective to the yellow line. It rises up to 1 volt. Of course, again, there are some minor differences with the simulation. This one doesn't rise completely up to 1 volt. It takes some time to build up until it finally reaches 1 volt. All these non-idealities are part of the parasitic or the non-ideal parameters of the components, and also there are some imperfections in the connectors, like for example, they don't have exactly 50 ohm impedance matching, and there are some discontinuities in the connectors as well, because connectors are not perfect, so every transition produces small reflections that will be shown in this graph. But overall, the signal response is pretty similar to what we expected from the simulation. So here I have added cursors on the oscilloscope on the horizontal axis, so we can see approximately how much delay there is. So as you can see, the delay between the first rise of the yellow signal, which is the output 1 or the channel 1 of the oscilloscope, which, remember, output 1 is the test point that is connected at the beginning of the trace. There is a delay of approximately 44.8 or almost 45 nanoseconds between this first rise and this second rise of the signal. In our simulation, this delay was exactly 40 nanoseconds because that was 2 times the propagation delay of our transmission line. In the real world, my trace is approximately 18.5 nanoseconds, but I have also some short segments of coax cable that add additional delay, and it's hard to measure that delay exactly, but clearly we are getting some extra delay. Instead of 40 nanoseconds, we are having 44 nanoseconds, so those cables probably are adding a couple nanoseconds of delay each one. And the delay between the rise of the yellow signal or the out1 signal and the rise of the out2 signal which is the purple line, is approximately 20 nanoseconds. So here you can see that this is also very close to the ideal or to the value we observed in the simulation, which was exactly 20 nanoseconds. Here we have 20.20 nanoseconds. So this confirms that our calculations about the propagation delay weren't that bad. They were fairly accurate. We can also determine that the characteristic impedance of the PCB trace is very accurate, because otherwise we wouldn't have obtained a value of 0.5 volts on this flat response of the yellow line. Remember that this voltage is the result of a voltage divider between the 50 ohm source impedance of the function generator and the 50 ohm characteristic impedance of the PCB transmission line. So if the characteristic impedance was very different to 50 ohm, this voltage divider wouldn't produce exactly half the voltage of the input signal. We will have a different value, either lower or higher, depending on if the characteristic impedance was higher or lower. So yeah, I think this tells us that even using a pretty low-cost prototyping service for PCB manufacturing, you can achieve pretty good results in terms of characteristic impedance if you follow the manufacturer's guidelines and stack up, and you design your traces to have the right width and the right separation between, the right spacing to the ground layers and all those parameters that we showed previously using the KiCad's calculator tools. Now, as an additional exercise, I wanted to simulate a more realistic circuit to see if the signal that we get looks closer to what we obtain on the oscilloscope. So what I did was I modified the T1, which represents the PCB trace. Remember, we used 20 nanoseconds because it was just a round number. I actually used a more accurate value for the transmission delay. I kept the impedance as 50 ohms, but I also added 2 more transmission lines to represent the coaxial cable segments that I'm using to connect the board BNC connectors to the oscilloscope inputs. So I estimated around 1.5 nanoseconds each. This value might not be that accurate, but I just want to get a rough number to have a closer signal to what we observe on the oscilloscope. So I also added a 1 megohm resistor in parallel, a 1 megohm shunt resistor, which is what the input channels of my oscilloscope have, and also an 18 picofarad capacitor, which is also what my oscilloscope input channels have. So let's simulate this and see if the signal looks closer. Okay, so I'm going to put this image side by side with a screenshot of the oscilloscope. So to make things easier to compare, I actually realized that I can change the color of the lines in LTspice. So I had them match the same colors that we are getting from the oscilloscope. And interestingly, after modifying the simulation to account for those extra transmission lines and the resistor and capacitor that are in the real inputs of the oscilloscope channels, we can see some similarities. Actually, the trace now looks a lot more similar to what we obtained from the oscilloscope. So, for example, this first overshoot on the yellow signal, it's almost identical to what we obtained from the simulation. So clearly, then also there is a little overshoot on the purple signal in both cases, and we can see also on the purple signal, after some period of time, there is some undershoot here, that we can observe in both. Of course, the amplitude is not exactly the same, but it is interesting that we observe these similarities in both images, and these additional pulses, or we can call it noise or ringing, it's caused because those additional components that were not in our initial simple simulation produce additional reflections. So these are tiny reflections that settle down very quickly, but you can still observe them. And in a complex board with other components, with a lot of traces nearby, you are going to observe a lot more of this kind of ringing and noise. And if you don't pay attention to those reflections, you can have like false triggers in your logic inputs or your receivers. Or if these overshoots are too big, for example, if the overshoot is too large, you can exceed the voltage tolerances, or the maximum allowed voltage of certain components, and that could produce damage or strange behaviors in some cases. So these are the kind of things that signal integrity engineers look for when dealing with high-speed circuits in fast signals, because unfortunately for these kind of circuits, high-speed interfaces are very problematic, and you need to be very careful when designing these kind of systems.
That is everything for this video. Thank you for watching and see you in the next one.